My name is Mehwish and I'm an associate professor in Télécom Paris, which is part of the big institute, which is Institut Polytechnique of Paris. And there are several schools within that institute. One is one that I am in. And my areas of expertise are mostly deep learning, machine learning with knowledge graphs or other kind of symbolic representations. So today in this talk, I'm going to give an overview of language models and symbolic AI, the research that I have been doing for the last few years with my previous group in Karlsruhe Institute of Technology, currently my group, which is in Télécom Paris, and some external collaborations. I many times do not know the backgrounds of the people, so I just give a little bit broad overview of almost whatever I'm going to talk about. So to begin with, all the work that you are going to see is with these many people. So University of Mannheim, our own institute, Télécom Paris, University of Bologna, SAP, and then my previous group at KIT. So you might have seen some of the faces down there. There are also students, professors, and I do not need to introduce all of them. So to start with, how many of you know language models a lot? So this is what I usually do the poll, so I cannot see you online. So I'm going to just introduce it anyway. So what has been happening in the language models is that started off as statistical language model, and I recently got in touch with one of the papers which was calling these statistical language models as large language models, which in this era feels like a little bit difficult to believe that this was very large. So the starting of these models was n-gram models and statistical methods, probability estimations. They were using these kinds of methods to do this kind of language modeling. So what we do in language models is that we predict the next word given the context. And then, of course, you have different variations like word to vec had, that given the context, you predict the word, and given the word, you predict the context. So these was the era of neural language models with word to vec, and you had GLAV and these kind of models. Then we had these bigger language models, pre-trained language models. You had LNO, BERT, unidirectional, bidirectional, and then came the GPT, which was still one of the pre-trained language model. And now we are in the era of ChatGPT. We all know about it. We all literally use it. And now it is easier for us to explain our research to the people who don't know anything about what was going on in its processing. So within this talk, I will be using these different kinds of language models and different kinds of words. So starting from neural to LLMs. And this is the broad category of what large language models are now. And this is still a slightly older survey, which is categorizing these language models. But now there are, of course, many more coming in. So you have now, for example, decoder only, where you have ChatGPT and these kind of models like Llama. You have encoder-decoder based. And then you have encoder only, which were like BERT, Roberta, DeBerta, these kind of ones. And then finally, we have the whole evolution of all the large language models which are out there. So this is from 2024. And you know that after that, there was DeepSeek. These were these reasoning language models which are going on, Gemini, Gemma. There are a lot of other models which came afterwards. So I'm not again going to go into introducing each of them. It's just that the whole field is really evolving really fast. And just in case, if you want to get updated, I recently found a list of language models on Wikipedia, which I gave the link on the side. They just keep updating whatever comes next. So this was like another way of way for me to start getting updated with what newer models are out there. And then these models are actually trained on different things, like you have reasoning models, which are actually trained on these reasoning chains from the other language models. So you have previously you had all the models which were using different kind of data. So you have web pages, you have conversation data, you have code data. So this is usually used for code generation, these kind of problems. Then there are many with scientific data which are able to also understand formula and these kind of things. For example, you have Galactica at some point. And then now you have these kind of plugins that you can add to these APIs that you can add to these ChatGPT or these models to actually enhance their capability, along with the external tool like browsing the web, these kind of things. So if there are language models, why are we talking about symbolic AI if language models can do many things? Of course, I do not underestimate their abilities, but we have several challenges. First of all, explainability is one of the biggest problems with language models, and which means they are black box, and it is really hard to know how they are doing these kind of decisions that they do. They are hallucinating, which is much lesser in the newer models as compared to the previous one, because the previous ones that were introduced, they had quite a lot of problems like toxicity and these kind of issues with these models in addition to hallucination. And there are many things which are completely implicit and we cannot know how and where it came from. We have this problem of provenance also, actually. So on the other hand, and of course, if a model is trained at certain date, it contains the knowledge up until that date, which means that you have always new knowledge coming in. What we want to do is to update these language models with the new knowledge which is there. So here in all these aspects, you have knowledge graphs which could actually help the LLMs. And then these systems where you have knowledge graphs, you have more structural knowledge, you can do reasoning because you have this schematic information. And then I think you have recently seen one of the paper by Apple about reasoning, and the language model was not doing really great with that. However, knowledge graphs are slower sometimes in these with symbolic reasoning because, well, they are symbolic systems and they are not scaling very well. So, so if you want to add domain-specific knowledge, you can add some kind of interpretability. And if you want to add evolving knowledge, for these kind of things, you have knowledge graphs which can provide LLMs with some support to do better. Maybe some other tasks, question answering is the most common one. But knowledge graphs themselves are not complete, which means that we need both the technologies together to actually get to something more concrete, to get to some better results, so to solve some tasks, stuff like this. So just a little quick introduction to knowledge graph, because from my lunch I sort of understood that many people already know about knowledge graph. So here in this image, what you see is entities and relations, the graph in that sense. So you have nodes, and these are the directed graphs which have labels over the relations as well as the entities. So it's a sort of more specific graph as compared to the graphs that you usually see, for example, where you have nodes and then just connections between them without any direction or labels. But in that case, these graphs are usually representing just the connections, and this always means one kind of relation. In this case, you have different kinds of relations, more semantics. So this is why it is called knowledge graph, and it is called multi-relational directional graph. So what we want to do, since I'm going to talk about some neurosymbolic approaches, is that we want to generate some kind of hidden representation, latent representation from this kind of graphs, which is what we call the knowledge graph embeddings. And we want to do different kind of tasks. We want to complete this knowledge graph. It can be head prediction, tail prediction, or relation. So here, if you see in this example, this would be the head, this would be the tail, and this would be the relation. This is the standard terminology which is actually being used. So I'm going to use that for now. And each of these things are predicted with the help of some confidence. So the systems output some confidence score for each of the predictions. So if it is 0.8, then it means it has a high confidence, and then this relation that is predicted is actually correct. So this is like the base definition of knowledge graph embeddings. And if you see here, I quoted the survey in 2017, which was the first survey. That's why I actually always quote that. And then afterwards, you have quite a lot of methods which came up, and there is this era was like knowledge graph embeddings everywhere. So it's quite a lot of approaches came afterwards. And then I will also discuss a little bit later on a little bit of a comparative study that one of the people did in the University of Bonn. But this is pretty much what is summarized in this survey with different kind of categorization of this method, like translation-based methods, semantic matching, these kind of methods. However, these knowledge graphs also contain different kind of multimodal information. So this was one of our surveys that we did in 2021. And then after that, the field still evolved fast. So multimodal information in this sense, you had image information, you had numeric information, you have textual information. And then why this kind of information would be useful? So if there are two artists which are close to each other, so just one thing to say here that if the entities are closer to each other here in the structure, they will be close to each other here. So similar entities will be close to each other in this embedding space also. So you have France, Italy, both are countries which are close to each other, and then relations could be together. So, but this is like just an example. So most of the time you have the similar entities. For example, Leonardo da Vinci is closer to Mona Lisa. So this is how the vector spaces are there. So continuing on that, if two artists have their word states closer to each other, then they will be actually closer to each other in the embedding space also, along with, of course, all the other information which is there. But if you take out this information, they will still be close, but lesser. So you have yet another attribute which will be actually helping that to learn better embeddings. So pretty much I'm going to focus on these kind of multimodal models for knowledge graph embeddings. So just to say one thing, that if you have any questions, do we take it at the end or do we do it now at the end? Okay. So here in this, you see one of the excerpts from DBpedia. And here you have the abstract information. So you have abstract for each of these entities. And then in actual DBpedia image, this relation was actually missing. So this work was actually done 2022. So in that data dump, this was missing, which is starting Leonardo DiCaprio, which is a very vital information. However, if you look at this description, you will find this information somewhere here. So of course, there are symbolic approaches which are trying to extract this information from the text and trying to add this to the knowledge graph, so you can actually process the abstract. But as I said before, that these symbolic approaches can be very slow sometimes, but actually most of the time. And then machine learning and deep learning methods have the advantage of learning from huge amount of data and generalize. So what we want to do is do this kind of prediction. So the good way to do that was what we want to do to start with learning representation about the entities. And what we did there is to not only learn representations just of the entities just with the textual information, but what we did is to consider the neighboring informations here. So we take the random box starting from one entity. Let's say we started from here and then we went like 3 hops here. This is just an example. In the experimentation, we actually did it with several hops, like 3, 5. So we did this kind of different extensive experimentation. And that this way we had the contextual information about the entity. So you know that in Word2Vec also these are the kind of examples that you see, that man is closer to woman in the vector space. So this way you get the context. Instead of a sentence, you have the structural information with the random box. And then what we did is to not do all the walks. So for example, if you start from one entity, you will have several parts out of these entities. And they can be really huge and it can blow up inside. So what we did is to do predicate frequency versus strital frequency to actually just select top 10. So it works similar to TF-IDF, which is, well, I won't need to explain, and the formula is actually the same, but adapted to knowledge graphs. So this way we were only able to focus on the important entities, on the important relations going out of each entity. So we had only focus graph that we crawled instead of crawling them all. And then we use our architecture that the paper was actually published in Semantic Web Journal, where we use this path information along with the entity description, and we learned their vector representation through encoder decoder. So attentive encoder decoder is like you can learn these. So attention helps you focus on the important parts of a sequence. So with this way, we learn these vector representations for the parts. For the descriptions, we use SBERT. So this is a fine-tuned version of the BERT. And then we combined, for each entity, we combined this information. And then we did similar for relations. But for relations, we actually did not crawl the whole graph. We used the tuples. And then we did the same with the tail as we did for the head. And then finally, we gave it to the distributed scoring function to score whatever it predicts for head and the head prediction, tail prediction, or the relation prediction. And then finally, we had our results where we compare with all the approaches which are using textual information. So for now, we are considering textual information from the multimodality part that we said. And then we were performing better in all the matrices which are out there for late prediction, and we used all the data sets which were there. So I'm not sure how much you are familiar with that, so I will just explain a little bit that there were some differences with these data sets. So here in this case, you had symmetric relations and inverse relations, because of which all the algorithms actually perform better, because there is an information leakage problem, because the information is already in the training data because of these relations. And then FB15K237 actually removes these kind of symmetric relations and inverse relations, and this way it is more there is no information leakage present. It's the same case with WordNet 18 and RR, but Yahoo 310 was already built in a way that it was keeping these kind of relations. So we performed our experiments on all of them, and there is a whole detailed appellation study with text, without text, because even with contextual information, we were performing quite well as compared to the baseline methods. So while doing this, what we found out is that these data sets may be good for doing using the textual modality, but they were not very good for numeric modality. Many of the entities, when we tried to look for their numeric information in the Wikidata or in the, WordNet, so let's say Treebase, it was not there. Then for WordNet, you don't have the numeric information because WordNet keeps the glosses of the words that it has. So these data sets were not really useful when we wanted to do something with the numeric information. So this is pretty much what I just said, actually. And what we did is to introduce our own data set, which was published in the resource track of ISWC. And we started with the Wikidata down. So here you can already see quite a lot of triples. And then what we did is to start from the numeric values. So if you have a longitude or a latitude information, we took those attributive triples, and then we went back towards that. So we took those triples, then we went several hops backwards towards some entities. And it was this way we created one data set. And in that one, we removed our inverse and duplicate properties, the symmetric relations that were the problem with the first data set. And this way we had our new curated data set, which was actually overcoming all the problems with the previous data sets that we had for the benchmarks. And then what we did is to create several of them. So this is the whole suite, let's say. So in the first one, for example, you can use for debugging purposes. So this is the smallest data set. Then we have the medium-sized data set, and the bigger one is for just checking the computational complexity of what you are doing of your algorithm. And then we compared, actually, the idea was to add more numeric values, which means to really test how sensitive the algorithms are to these values, which were proposed before for the numeric values. So I'm not sharing the results here, but the results were fairly obvious. That should happen, actually, is that on our data sets, the algorithms were performing lower as compared to these feeders and these kind of other data sets which were out there. So we extended it to multilinguality. This work was halted because I changed my lab, so we didn't continue with this. But we are coming back towards multilinguality slowly. So we made it for English, German, Russian, and Chinese. But for English, it has the abstracts for all of them, which means it can work for textual as well as numeric values. Same for German, we had 88%, quite a lot of entities had this kind of information, even on the bigger data set. However, for Chinese, we were suffering a little bit, but this is usually the problem with the foreign languages. But what you can do is to go to Wikipedia and extract the abstract information from there, if they contain it. So far what I discussed was all transcriptive link prediction, and none of the approaches were taking into account the interactive link prediction task. What happens there is that you have unseen entities in the test set which are not in the train. So now what we want to do is to do link prediction over there. So same is the case with not just entities, but the relations. So we took care of both of them in our new work, in our base approach that I'm going to talk about. And this is pretty much what this image explains. For example, here we have seen producer, but here, for example, in this entity, it has a producer, this one, but this link is not already present there. But it is present in the test set because you have this kind of movie here, which has the producer, Christopher Nolan. So this way you have some kind of relational information which is present in the test, but not in the training set. And then in this case, we actually focus on the relational part more than the entity part, because here, for example, we learned the representation with the help of BERT. We learned the representation for the abstracts, for the entities, but we wanted to focus on the relational information. And then what we did is to create a graph of relations only. So if one relation is reachable to another relation by some number of hops or some paths, the number of paths will become the weights in the graph, and then you have the connection between those relations. So this way we created our graph, and then we use simply node embeddings, which are actually only considering the weights and the weights on the relations and the nodes. So here also we use the standard data set, which was there, 5 million. Wikidata 5 million is used for inductive link prediction quite a lot. But the problem with that is it was mostly for entity prediction, so head or tail prediction, but not the relation prediction, not for doing the inductive link prediction over the relations. So we curated this data set to our needs, and then we did our algorithm as I described before, and we had better results again. That's the race that we do with the link prediction. And then if you see closely, the results are still not that better. So these numbers are still very low, even though we did better than the existing ground truth. So there is still room for quite a lot of improvement there. And these are fairly simple methodologies, and then our algorithm performs better, but still you can see the numbers are quite low. So Okay, so all of this that I talked about are the link prediction tasks over the factual information. None of them is still using the semantics. And all of them are using like neural models or the masked language models to learn the representations of the entity, the labels of the entities or the abstract of the entities. So I'm just trying to zoom out a little bit. So these were towards the methodology side, towards the framework side. But what we wanted to do is to know if we can apply it to something. Can we use them as an application? So what we did is that we started with our scholarly data. This work was in collaboration with the University of Bologna, where they had the whole network of open citations. And then we use that for author name disambiguation here. Now here, what you see, you have an column here and an column here. So you might have, I'm not sure how many of you had this experience, but in Google Scholar, sometimes the papers pop up which are not yours, which happened to me here. For example, I don't work with the biomedical domain that deeply, and I wasn't at that time it was even less. So I was happy to see one morning that I have bumped in my number of citations. So it's at 1485, wow. And then I was like, okay, there is something wrong. And then I started going towards the citations that I had, and I found out that. So, of course, like a good scientist, I actually removed it from my Google Scholar. But then this is one of the problems that you see quite often. So what we did is we wanted to see if we can use this kind of techniques for actually these kind of problems that we are seeing. So this is still multimodal, and it is using existing technique, but it is applying it to this whole network that I'm talking about, the open citations. So you have papers which are connected to other papers because you are citing them, and then for each paper, you have the information, title, abstract, authors. So currently what we did is to put that together. This could also be separated. You can have citation networks separately. You can have these author networks separately, and then you can combine that. And this way, it could be more. It might be better to learn it this way. But for now, at that time, we just started with combining all the information together. And then here, in this case, what we did, we use LiterallyWikidata, which builds upon France E and uses the numeric triples. So here, it does not consider the context. It just considers the triples as is. And then you have the titles and the numeric features. So what actually literally does, it defines a function over these numeric features. I'm not going to go into the detail, and it learns what is there and then improves the embedding. So just many people get confused that why not represent the numbers in the embedding space. So I have my own views on this, but there are some people who are turning these numbers into entities. There have been some recent works. So, but in this case, it is actually learning what is in the number and helping helping to improve the embeddings. So you have titles, and then we use Spectre. Now, Spectre is the fine-tuned version of Word over scientific articles. So this made more sense to use it for us instead of using the whole Word. And then what we did, we learned the author embeddings and the document embeddings. Well, it was within one stage. So we have, this is just to show you that we had this kind of information. And then we did LNFI blocking prematurely on the data just to separate. So what is LNFI is that last name, first initial. And then we did clustering within each of these blocks. So it was much clearer and easier to do this kind of hierarchical agglomerative clustering based on these LNFI blocking. And then this way we obtained the clusters for who the names were closer to each other. And this way each cluster was containing those authors which were working on similar things. So for example, if suddenly there is an outlier in my work which is talking about biomedical data, it may happen in future, but if there is lesser 1-2 publications which are coming out of nowhere, then it means that this MLM would be somebody else. So this way we did this kind of clustering, and finally we had our results, which were, again, as usual, we were good in the race, so it performed better, but I think this method was really giving quite good results to us. So if you want to access the code and the data set, because the data set itself was not very, so there are two data sets. One is open citations and one is A minor, which already exists, but open citations was more into what we, the problem that we wanted to achieve. So all of this that you saw, there are other applications that I did with the knowledge graph embeddings. For example, co-reference resolution with the Friendster. So this was another linguistic linked data that we published. So I'm actually sort of not talking about this for now. So all of this that we saw, transductive link prediction, inductive link prediction. Now there is also dynamic link prediction with the dynamic knowledge graphs. But what this study that you are seeing right now is doing is taking all the algorithms which were there for transductive link prediction, and then they are comparing it by doing the hyperparameter optimization. So this is all what they did, and this was published in IEEE Transactions of Pattern Analysis and Machine Intelligence. So it's quite a good journal actually. And then this is a thorough analysis of all these algorithms, and what they found out that even with hyperparameter optimization, you get comparable results like with Cars-E, which was one of the first models, as compared to the models which were coming afterwards. So it turns out that all the effort from the beginning that we were doing actually went to a little bit of a waste, but still the newer models were doing slightly better as compared to the older ones in some cases when you had a little bit different of a loss function. So I really recommend you to look into this paper. And there was another paper in ICNR, I think, which was talking about similar kind of hyperparameter optimization, where Trans-E was actually outperforming, let's say, REST, for example, which is using tensor factorization. So all the things that we saw by now is always talking about factual information. So you have head, tail, and then relation, and both are entities, and then there is a relation between them. But what about the taxonomic information? So you have different kind of information, type information, taxonomic information, and the semantic information. So let's begin with type information. And what we want to do is to predict the type of, for example, one entity. Now we are going a little bit from broader from what we already have. So, for example, here, this coming back just a bit. So we have Leonardo da Vinci. The type of this could be human or person. But keep in mind, if you say artist, it can also be a role. When you try to represent it in the knowledge graphs, there's this type of discussion that keeps on going on for the community. So here I would say that the type of Leonardo da Vinci is a person. And then what we did is that this was our collaboration with the University of Mannheim, where we used different variations of RDF2Web. And then there, in this case, we did classic normal walks that I was talking about before also. Then node walks only contain the node information, edge walks only took the relation information, and then we learned their embeddings using the embeddings of the entities based on these things using different variations of RDF2Web. And then we have similar thing for the entity description. We didn't change that part. And then what we did is to try to see what happens for entity typing here. So we treated that as a classification approach. I will just skip that slide for now. And then we did our multi-class classification and multi-label classification. So if I go back to this, each time where we were combining all of this information, the relation information, the node information with the description, we were performing better. And then there is one thing that we did here in the graph is the local and global PCA. So here we did dimensionality reduction to the knowledge graph that we had. One was based on the data set that we had, and the global PCA was based on the whole knowledge graph that was there. So we did this kind of dimensionality detection and see which one performs better. So of course, local PCA was performing better in combination with these kind of techniques that we use for the walks and the description in the question. So here I will just quickly mention this one, because I will not go into the detail of this. So what we did, instead of using the graph walks, what we did is to create a network of Wikipedia categories. So what we did, we took the entities from the data sets and we said, why not use the taxonomical information that is given in the Wikipedia? So here you can see they look like this: American films, 1985 films, and then each time the two categories had some entities in common, we built a connection between them, and the weights were actually the common entities between the two categories. And then this way we actually learned the embeddings of those entities which were within that category. And then we combined it with these embeddings. So you have textual embeddings like mass language models, these kind of language models which are there. So word to word, glove, bird, Wikipedia to word. Now the thing that is very interesting here, if you can guess, which among these models like bird, word to word, glove, and Wikipedia to word, which one would have performed better? Any guesses? Why?
There's a context. Isn't it better?
Yeah, so Wikipedia to word is better because we are working on Wikipedia and it is coming from Wikipedia. And we are using Wikipedia categories. So it sort of felt like cheating, let's say, when we got the results. And I'm like, okay, no, that's not going to work. So we just actually excluded those. Well, these are still reported in the paper, but I think this is not a very good idea. But still, we had our own architecture performing better than the baselines. And in any case, if you do not use the descriptions, if you are using descriptions and you are using the abstract, of course, BERT learns their representations better. But when you have the labels of the entities, usually word to word outperforms, because word to word is more capable of taking care of like a word or labels like shortcuts. So these are some of the lessons that we learned from this approach, actually. So up until now, I talked about factual knowledge, I talked about type information. So we are slightly moving from the factual information to more semantic information. So what we started with is that recently, last year, we published a new version of our Yahoo. I'm pretty sure many of you already know this data set because this comes on and off. And what we did is that we thought, okay, Wikidata taxonomy, we tried to actually analyze it, and it was not really curated. It was really like badly created because, well, many people can actually make the changes there. So what we did is to take out the first two levels, the initial levels of the taxonomy, and we added the taxonomy from schema, therefore. Now, even if you do that, it needs a whole reorganization of everything. So what we did is to did many kind of curation techniques. So I didn't let you to look into the paper for that. Curation techniques to actually reorganize Wikidata within this taxonomy. And then the problem was that we did this kind of curation, which was on the higher level, very manually, which is extremely time consuming. So we went through the examples ourselves. So here is just an example of what we had. So we got the schema.org here, thing person, then we created some of our own classes. So you had worker, creator, then you had musician, which was coming. So if it is in blue, it is also coming from Wikidata. So it's like a mix of everything that we did, but it was quite a lot of effort to actually do this curation for Yago 4.5. And then it got recently released, but then we thought, why not LLMs? Why don't we do that? So we moved on from manual curation to the curation with the help of language models. So it's sort of, if you see that there are, I think this is the example. So what happens in that is you have hydrogen, which is some energetic material, and then you have chemical element. In many cases, for example, you have city, which is spatial entity, which becomes geometric object, which becomes mathematical object. If you do the inference in this way, city is not a mathematical object. So you have this kind of problems there. And then there were many links which were actually missing. So it should be here. The link should be here, but it was only this one. So we had quite a lot of ambiguities, sometimes many things which were both classes as well as instances. However, in these representation techniques, you have a way of representing class, something as a class as well as an individual, because it's this is what we call outputting. But Wikidata does not follow that technique. So we said, okay, this is at least on this side, we consider that as an error, because each time when we saw such kind of entities, they were either used only as entity or as a class. So which means there was the error on the side of Wikidata. So what we did is we took the taxonomy and then we rewired the taxonomy actually. So we did quite a lot of refinement on our own. So if there were classes which were empty, we removed them. There were many empty classes actually, which if you look at the, if you take the top-down approach to the representation, is not a wrong thing to do. You can have classes which are empty because you are trying to define a domain top-down, and you can have entities which could come afterwards, and as the knowledge graph evolution part. But for this one, we consider them as like not useful, and then we removed them from Wikidata. Then if there were some links where you had less than certain number of entities, we removed those kind of links. So we did some kind of curation over that before we asked LLM to actually give us the relations. So what we did is that we took two classes, and then asked for a relation between them. And we did it with the help of, we provided instructions, and we used mixture, which was instruction tune. And we actually corrected quite a lot of things. So it was like simple zero-shot prompting was already helping us quite a lot. So this paper was actually recently last year accepted in the second. So here we did two kinds of evaluation, which is actually in line with what was happening in Yahoo 4.5 also. So here what we did is to do some kind of intrinsic evaluation, we call it. This is like not really evaluation over a downstream task. So here we did the verification of this taxonomy of these things memory. So you have like classes which were before 4.1 million, now they were 17K. Really less than before. Then we have top level classes which were 38, and in our case after the refinement we had only 16. So this way we reduced quite a lot of clutter from the Wikidata. We might have lost some information. Definitely it's not the ideal way to do it. That I agree with that, but still it was afterwards more curated as compared to what was there before. And here we remove the loops. So if there were loops, we straighten them. We remove redundant link, which was, you do not need an LLM for that. You can do it yourself. And then there were classes which were 3.9 million, which were actually without instances, and now we have none. Yes. And then we improved a little bit of understandability. And finally, we actually took out all the instances from each of these classes and performed entity tagging over there. So we re-instantiated the new taxonomy that we had from the Wikidata over several depths. So you have 0 to 5 inclusive, and this way. we did our entity typing. And then what we did is to confirm, use LLM as a judge to check with the typing accuracy. And here in this case, over original, it was much lesser as compared to what was with our taxonomy, which was there. So, sorry. Yeah. So this is the work that we recently did, and now we are continuing to see other LLMs also, because after that you had reasoning LLMs, things like this, and they have better, of course, they are more curated, so we are trying to see if we can provide a better version of these taxonomies and see what happens. And then side by side, we have just another recent work where we took the existing taxonomies and started enriching them with the help of LLMs. So this is what it is doing is to go level by level with using the depth first or breadth first search. And then each level for each node, it is generating the children's, and then what is happening, it is combining that with what is already existing. If it already exists, we do not take into account. If it doesn't, then we add it. And it should not be present on the previous level or the next level. But we did not check the whole branch yet. So we started to do this with schema.org. And then what happened is that at some point, it started generating the instantial information instead of giving the subclasses. So what we did is to use Wikidata as our like hallucination detector, let's say. And then what we did, we checked the Wikidata if this is an instance or a class in Wikidata. If it is an instance, we don't take it into account. If it is not, then we take it up as a subclass. But the problem with that is that Wikidata itself has some problems, because many times what we saw is that we are seeing that it is a class, and it is still telling us that it is an instance of another class. So this one, there are some erroneous things within Wikidata. So this is one of our future works that we want to take into account. Also, when we were trying to generate the sub concept, the subclasses, we also checked the similarity of what was generated with the actual class that we gave, because sometimes it was completely different. So this is how we did small things to actually get on the relevant subclasses. So we have quite rich schema.org taxonomy, and now we are working on making it properly, like doing the evaluation properly with human in the loop. So this is the kind of thing that is ongoing with this project. And we are using some kind of taxonomy expansion techniques to actually learn this here. The idea is to expand this to other taxonomies. So here in this case, we will be moving towards biomedical domain, because you have these kind of taxonomy, you have UMLS and these mesh, these kind of taxonomies, and they have been there for quite a long time. So we want to see if it is applicable to these taxonomies which are out there. So, so far we have factual information, type information, and the taxonomical information. So here we are gradually increasing our difficulty from a very low level of semantics to a bit on high level of semantics. But whatever we saw in the factual and the type information, it isn't semantics, because there is then ontology which has classes where you have relations between other classes, these kind of things. You can do several kind of reasoning things. So actually this is pretty much what it means, that what are semantics, which means that we are not yet using the RDF schema. So now there has been recent work, a lot of work which we summarize, I will just move here, which we summarize here. I will come back to this slide afterwards, which are considering this kind of information, the OWL ontology, the RDF schema. So what is happening there is that you are able to present such kind of concepts. So you have C is subsumed by E, so you can represent this concept within this embeddings that you saw. So what you saw so far was what the Euclidean spaces. Now we are moving on towards the box embeddings, which are representing the concept as the boxes. So here in this case, you can represent these kind of concepts which actually keep the semantics as much more than what you saw before in the Euclidean spaces. So you had, for example, here, there has to be something common between C and D, which is E, which is subsumed by E. So here you have a space which is common between C and D, and it is actually subsumed by the box C. This way you are representing these kind of concepts here. So here in this survey, so there was supposed to be an animation here which got lost in the PDF. So you are seeing this thing here already. But what you see here in front of you are the different embedding approaches which are considering these levels of semantics. So you have OWL, you have these box embedding based. So these are, for example, OWL2Vec is based on doing graph walks over the schematic information. And these box embeddings are using the comps, and box2E are using the box embeddings for that. And these are taking care of these constructors that you see on the side. So you can already see, I think, in this case, you do not have many algorithms which are taking care of these ones. So you have this role composition, these kind of semantics. Then you have the bottom concept, which is not really represented in any of them except for cat E, for example. So there is still room for improvement. Now my question here is, can we do this with LLMs? So can we already, the downstream tasks that we are actually solving with these kind of semantic embeddings, can we do this with LLMs? So it is mostly like schema completion tasks. So you have relations, you have classes, these kind of tasks that you can solve with these kind of embeddings. So, so this is still evolving field. That's why I moved very slowly from factual to type to taxonomy, and now you have box embeddings, and there are some people who are also working on cone embeddings. This is to represent this kind of semantics there. And then just everything that uses knowledge graphs or graph data towards tabular data, which is very common with the biomedical domain, is that okay? Yeah. So biomedical domain. So this is we try to do something a bit more general, where we try to do a bit more general, where the people can upload their tabular data into this system that we have, and then what it does is that there is a claim that this table that you upload here, for example, and there is a claim. We want to know if the claim is actually inferred by this table or not. So what happens in the traditional approach is that it reasons over the data in the table and gives you yes or no. So this is what we get pretty much with LLMs. So this way we use several kind of prompting, and then it was like chain of thought and zero shot, these kind of prompts that we already embedded in that, and it gives you true and false. And then it is able to actually also work with the multimodal data. So we included some OCR techniques there. So the most common one is the Symbolic that everybody uses. So this is all happening in the real time. So so this is one of the papers that we have in LLMs, which will be actually presented this week by one of the students, which is there. And this was actually part of our course that I'm teaching in Télécom, which is language models and structured data, where we are talking about graph, table, or other kind of any kind of structured data that you can find. So this is just a screenshot of what is happening. Not only does it do this kind of claim verification based on the table that you have, it also highlights exactly which cells of the table are actually helping in this claim. So it became a little bit more explainable for the people who are trying to do these kind of tasks. And then we are also currently including the entity link tool to this. So the entities which are there, they will be linked to Wikipedia. In some cases, it automatically does it, but many, I'm not sure how many of you have tried this entity linking with the help of LLMs. It just gives you random Wikidata IDs or Wikipedia pages. So we are currently also working on this. So this is some of the things that we have currently, and there is just a comparison between different tools which is out there. So in our case, we already have these kind of models already running, like as a real time ongoing. It is so what we did is to take the smaller ones, because if we do the bigger ones, our servers will not be able to support this. So for now, this is what we have implemented, and I think it is quite great that we are able to run it online like this, because many of the company data is also a tabular form. So yeah. So what is ongoing now here for these are some of the things that I had been talking to you in the breaks or things like this. So one of the things that we are currently looking at is the information extraction, where we are, this is what I call knowledge intensive tasks here, just to generalize. What we are trying to do is to look at the shuffle constraints for this. So here you can give the constraints on the domain and range of the relation if you extract it. So if the relation is extracted from the sentence and then the domain and range are completely off, which are given by some constraints that we have, then it means our relation extractor is not working very well. So this is one of the things that we are doing with the India Sociantipolis. That's the group of Fabiano. And then we are trying to generate logical axioms from the textual data. This is another one which is going on, which is not really on knowledge graph. That's why I said symbolic AI, because we are touching upon also tabular data and logical data, these kind of things. Then one of the work that we are doing with Nokia Bell Labs is mostly on the temporal hallucinations and dynamic knowledge graphs. So we have noticed that many times the rate of births and these kind of things still in the newer models are wrong. So we are trying to look into this. These are all ongoing work, because my group just started like 6 months ago, or let's say not 1 year ago, things like this. So we have quite a lot of things in the pipeline. Then we have also happening hallucination detection. This is also working with information extraction, but what is happening there is that it is on the biomedical domain, and there is a taxonomy of hallucinations. For example, if these are factual hallucinations, if these are logical hallucinations. So there are several types of hallucinations, and what we are trying to do is to classify these hallucinations and then propose the mitigation strategy. So it is, of course, working with information extraction, but with mitigation strategies. So it is taking it a little bit one level up. So now, so these are the things which are still happening, and what we are starting to do is to work on cognitive aspects of language models. For example, we are working also on theory of mind. We are working on finding knowledge conflicts with Eurocom. So we have quite a lot of, I have quite a lot of collaborations going on in different topics of language models, large language models this time with knowledge graphs or other kind of symbolic information that we have. So thank you very much. I hope it was not too heavy. So this is pretty much what is going on.